Well, hello everyone. We are even smaller than usual. We are a small group today. That's okay. I appreciate you're here. Um, yeah. So, as I already mentioned, there's no lab today because I don't want you to get sick. So, there you go. No lab. You're spared. We'll do that one after the test. It's a cool. I like the lab. It's sad, but that's okay. It was center mass stuff. I posted. Ooh, did you also catch a sickness, or just precautionary?
Just precautionary.
Smart.
It might just be bad allergies.
You're a smart man. You're a better man than me. Anyway, sorry. Practice exam, great. I posted it. At some point, I guess I'll also collect all the clicker or top hat questions and mix up the problem set or whatever. But yeah, don't use the practice test as your own. Like, if you haven't done the problem set problems, the practice test is not enough practice. Each topic has like one question dedicated to it. So like there's 8 questions on fluids in it, and the reason for that was so I could hit as like all the topics basically. But there's only one question on each topic. And same with momentum. There's like, yeah, it's good. It's useful. I think I'm glad I was able to make the practice test. But I would say that it is, it's not just don't use it as your only thing.
Is there any style of question that we'll see on the actual test that's not on the practice test?
The only style. That's a good question. Was there any style on the actual test that's not involved in the practice test? The only one I can think of, and it's on the practice test, just the answers are presented a little differently, is one where I say, if I double this and triple this, how does this get affected? And so, like the easy one that I can give you all is like, this isn't for this class, but like for this test, but if I triple F and I double the mass, what happens to the acceleration? And the answer, you do F equals ma, A equals F over m. You then plug in the 3F over 2m. And the final answer is my new acceleration is 3/2 my original acceleration. So there is problems like that on the practice test. On the actual test, I presented the answers kind of like in this format, like that the new one is 3/2 the old one. On the practice test, it's in like words. It says like the new force, like there's a piston problem. So, I'll just pull it up. That's easy enough to do. So, piston. Oh, there's this one too. A theme park is testing a new roller coaster. And I'll zoom in way more on that. If a coaster car is released from the same height, how does doubling its mass affect the speed at the bottom? So but again, it's all like the speed doubles, the speed triple, as opposed to like V2 equals. So it's there, it just looks slightly different. This is another one of those. If I want to quadruple the output force, make the force 4 times bigger, what should be the relationship between the areas of the small and the large piston? On a test, I would say A2, I'd call the large piston A2, and I'd say A2 equals 2A1, as opposed to this wordy thing. But otherwise, I'll be straight up honest with you all. How did I generate these? I took all your quiz problems. I took the test that I made for you all. Test 2 is largely made. I just need to double check things and then start printing it. And I said, ChatGPT, make different problems. And it did an okay job. There were some of these I had to go through and like change some of the wording and do things like that. But I tried that out, and it seemed to work decently. Again, this one's super wordy, but whatever. The test, I generally avoid this wordy of answers because I don't want you to spend a lot of your time reading. But yeah, that's why the style of it looks like the quizzes and the test, is because it's based on those. So, and also, yeah, when you hear me say that I used the actual test, if you don't know what you're doing, So it's not like if you just print all these questions and stick them on your note card, that ain't going to do it for you. Because the ones on the actual test are solving for different variables, are in different contexts and things like that. So anywho, all that to say, these are great practice ones. These are going to test whether you understand the thing, but I do not encourage you to print out the answers to these and put them on your note card. You can if you want to, like go for it. But I think that's kind of a trap that I don't want people to fall into. All right. Any other questions about this? The other thing you can do with this is kind of time yourself. Again, the difficulty level here is mostly the difficulty level, maybe a tiny bit more, but not, if it is more, not really much. I would say difficulty level here is pretty similar to the difficulty of the test. And so you can time yourself when doing this and see how long it takes you. There's another kind of practice you can do with this. So anywho, and you can ask me any questions you want. And there's 2 versions, answers, all that good stuff. Okay. So today we're going to finish fluids. And then at the end, I'll try to make a big old bullet point list of like the concepts that you need to know. Because there's a lot of concepts we've talked about in fluids. And so I'll make a big old list of kind of what's the key things here. So last class, we talked about pressure. Maybe that was 2 classes ago. Pressure is not force. Pressure is force over an area. Why does that matter? It means, and so just kind of jump down, the consequence of this that was kind of really interesting was this whole piston thing, where if you have 2 pressure, so a change in pressure in a system gets applied everywhere. Yay. Why does that matter? It means if you have 2 pistons, you can multiply the force. That was the really cool byproduct of this. This pressure gets applied everywhere. If you have a bigger area, you get a larger force. So like the one in the practice test, how do you make a force 4 times bigger? You apply the pressure to an area that's 4 times bigger, and it works out great. And so we did a problem with that with a syringe. We also talked about that, like the weight. How do you get pressure? There's lots of ways, but one of the easiest ways is just have a fluid with some depth. And then my beautiful picture here shows that it doesn't matter how wide your container is. A straw, a big old cylindrical tank, the ocean, the pressure is the same if you're the same height down inside the liquid, which is something people don't expect. It's one of those like weird things that feels off, but it's true and it's really cool. And we showed the math for it and all that good stuff. We talked about like, yeah, if you measure the blood pressure of someone farther down in their body, you will get a larger blood pressure. If anyone ever wants to test that, that would be interesting. I don't have I don't even know what they're called, the cuff and the thing and the pump, whatever. I don't know if you all have a way to test blood pressure at home, but if you do, try it out. I'm curious if it would, you could literally see if if you go 0.5 meters down, how much does it go up? My expectation is it won't go up this much because there's a little bit more going on in the body and there's like capillaries and stuff but who knows? Again, I don't know for sure. All right. Okay. And then the last thing I think we talked about. No, it wasn't quite the last thing. Well, kind of sort of. The buoyant force. And this was discovered like forever ago. And it's such an easy calculation, which I think is so cool. If you have something in water sinking, like it's fully underwater or it's floating, it doesn't matter. It doesn't matter how much of it's underwater. The amount that the water pushes up on it, the buoyant force, the thing that keeps boats floating, the thing that makes you weigh, quote unquote, less underwater, you just take how much fluid is displaced, the mass of the fluid, times G. And that's how much the force is upwards. It's like such a simple equation. And I think it's really cool how simple it is. We did an air mattress and saw how much it could hold if it was fully submerged. And then this thing's pretty important. This one's cool. If something is floating, you can find the density of that object just by seeing how much of it is above water / below water. So, really easy example here. Actually, let me just give you a problem with it. Let's practice this one. It's so easy to practice. An object is 20% above, floats on water, and 20% of it is above water. You know what? Let's make it weird. 17%. What is its density? All right, and the possible answers are 83 kilogram per meter cubed, 1700 kilogram per meter cubed, 8,300 kilogram per meter cubed, 830 kilogram per meter cubed, or 170 kilogram per. Great. And I'm going to double check everything before I ship it. See if this makes sense. This is an important one. Must hunt. Oh, and I will warn you, currently this equation's not on the formula sheet. I don't know if I'm going to add it or not. It's kind of wordy, which is maybe a cop-out. I may or may not add this to the formula sheet. I don't know. It's kind of derived from the buoyant force, which I did add. Go for it. This one doesn't require that much math. I think most people. Okay. Yeah, that's fine as well. All right. We'll go like 10 more seconds or so, 10, 15. I can maybe wait a little longer. We're still chugging. All right, I'll wait a little bit longer. I see people still working on it. All right. In 5, 4, 3, 2, 1. All right. So again, this one's really nice and straightforward. If 17% of it's above water, how much of it's below water? Yeah, 83% is below water. Below water. And then, so that means 0.83. If we like write this out mathy-wise, momentum or the density of the object over density of water, and then the density of water is 1,000. So 0.83. So the answer is 830. Yeah, it's a really like nice, works out really nice. If you do the math, 8,300 would mean it's more dense than water, which means it sinks. 83 is like super tiny. That thing would be like sitting on top of the water basically. And then yeah, the 170 and 1,700. That's just, so remember fraction submerged equals this. And that hopefully makes sense. If a thing floats on water, as this number gets bigger, my object's going to get less dense, and you can kind of see that relationship and all that good stuff. So, all right. Peter's got a joke.
I looked up the definition of opaque.
but it wasn't very clear.
That one's very good for optics, which hopefully you'll learn in physics too. Anyway, all right. The next thing we learned, and this one probably felt a little weird. It felt a little weird trying to like get the idea across. But here's the idea: you go in water. Do you feel like you weigh more or you weigh less? You weigh less. Why? Buoyancy. So basically, they make up something called apparent mass. That's like how much you. It's not. Remember, mass is not weight. Mass is not weight, but if you multiply it by g, it becomes weight. Your apparent mass is like if you had this much mass, that you'd weigh a certain amount if you're underwater because the water's pushing up on you. Apparent mass is how much you weigh, quote unquote, underwater if you multiplied it by 9.8. And it's just the mass of the object minus the mass of the fluid displaced. Why? So let's just like apparent mass apparent equals mass of the object minus mass of the fluid displaced. Great. Let's just chuck G in front of everything, or to the right of it. This might be a little easier to understand. If every term has G, the force apparent, like how much it seems like you weigh underwater, equals how much you actually weigh minus the buoyancy force. It's just a free body diagram kind of thing. Gravity pulls you down, buoyancy force lifts you up. You add them together, you get how much you're actually being pulled down. You have a free body diagram. Gravity pulls you down, buoyancy force pulls you up. If you subtract, they're not going to be equal to each other if you're sinking. And so what's left over is how much you like effectively weigh. And if you just get rid of all the G's, it's just masses. So that's the idea, y'all. Yeah, and it's convenient. It's used to find the density of various objects. I think we did a problem with that. Yeah, right after this. It even gets its own section. I don't even know how I did that. That's so weird. This is going to be a bad idea. Did I just delete all those slides? No. Yay. All right. So we found like the density of a woman in water. So this is a good problem to kind of practice this. So we found in part A, we found their apparent mass. Then we found the volume of the fluid, which is the exact same as the volume of the person. Then we found the density of the person. And then then we did a whole thing with, all right, let's shove some air in their lungs and see what happens. And it changes their density. Now they float and all that good stuff. All right, great. How many slides left do we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 slides. So the last things I'm going to teach you all, again, there's 2 more concepts, I think. 2 more concepts, 3. Let's say 3. I need to teach you. All right. I have a beautiful picture. Some fluid is traveling in a pipe. What will happen to the fluid's velocity if the pipe gets smaller at some point? You all have lived in this world. You've played with hoses. You should be familiar with this. If not, that's okay. I want to warn you, pressure decreases. That's actually the last topic I'm going to teach you. And that it's totally counterintuitive. Now, pressure doesn't have to do with velocity. When you put your thumb over so water's coming out of a hose, great? What happens when you cover up and you make the area smaller? There you go. That's what's happening here. If you go from a big area to a small area. Yeah. But when things get faster, we're going to learn that results in a lower pressure, which is a totally separate thing that I'm going to have to try to convince you of. That's going to be completely separate. Don't worry about that one for now. It's the last topic I'm going to teach you, and it's one of the most counterintuitive things. Yeah. I'll do my best to convince you later on why conservation of energy is the easy answer, but we'll see it later. All right, we'll close this out in 10 seconds. Yeah. I'll count really slowly. No, it's faster.
That's what I said.
Yeah. It is. Yeah, it's faster. You said the pressure was higher.
Okay, I got that.
Pressure and velocity aren't going to be, yeah, that's what I was correcting. It's faster. All right. I'm just going to leave this open because, great, what happens, y'all? You put your thumb over the end of a hose, what happens? Doesn't, okay, sure, it stops if you cut, it's pretty hard to do that, to stop, you can, probably. Anywho, what happens, y'all? Does it go faster or slower? Great, okay, I'll just leave this open. The reason I'm leaving it open is because I've been saying the answer over here and I'm in front of the computer, and so anyone online got the answer, and I don't want people in class to not, great, you know this. Have you ever thought about why? Probably not, well, it's a good question. So, is it because the pressure builds up? So, I'm going to give you all a little bit of a foreshadowing of something we're going to learn in a few slides. It's the last thing I'm going to teach you, and it's the most counterintuitive thing in all of fluids. The pressure in this faster section is lower than the pressure in the bigger section. No, you're fine. It's one of the most counterintuitive things, and it's going to be the last thing I teach you. But that's a great point. It's not because of pressure. It's because of a certain special quality about fluids. They can't be compressed. And so why does that matter? As this water is going in here, it's basically trying to be compressed. That's the idea. It's getting to a tighter space. But the problem is you can't squish those water molecules into a tighter space. And so the analogy I'm going to give you all is cars. I'm going to give you all an analogy of cars. Let's pretend this is a 4-lane road. Nice big old lane road. There's 1, 2, 3, 5 lanes. That's too many. Whatever. I don't care how many. There's a bunch of lanes. You got cars driving on those lanes. There's so much more room. So they don't need to go as fast to fit as many cars and all of that. But say I have all these cars. Great. When they get to this narrow thing, if they go the same speed, what's going to happen? They're going to all build up on each other. They're not going to be able to make it work. If I have a 2-lane road, for me to fit all my cars on that without them backing up, they got to go faster. For them to have the same, you can think of it as throughput. If all these cars reach this thing, if they don't start speeding up, if I want to fit all these things on here, they better be moving because I got cars behind them. And if these cars do not get out of the way, what's the end result? Yeah, they're going to pile up. The fluid would pile up here. But if the fluid piles up here, what's going to happen? The end consequence is the water in the pipe would stop moving. And does that make sense? That when water reaches a tight thing that it stops moving? No. So the way we avoid the water stop moving is it speeds up so that more water, let me rephrase that, the same amount of water can fit in a narrower area. The same amount of water has got to pass through this thing. Think of a river. Another example is a river. A river is a fluid. If a river is really wide, I have a certain amount of water traveling through it. That water then, that river gets really narrow. My water still's got to move. The same amount of water still has to travel down that river. If the water doesn't speed up here, then it's going to build up here. And that's not what happens. When water gets to a narrow thing, it doesn't just like overflow on the banks and like spread everywhere and all that. It just starts going faster because the water behind it's going to keep pushing it forward. So all this to say, it's got to go faster. Otherwise it's going to clog. And they don't clog. Like that's not what water does in a pipe. And so the next thing I'm going to teach you all is something called flow rate, which is exactly what it sounds like. It's the rate of flow. So the flow rate has a symbol Q, and it's really simple. How much fluid passes through a location in some time? If we think of our car analogy, it's how many cars pass some point in some time. The symbol for this is Q. Why? I have no idea. The units are exactly what you expect. It's volume per second. So this is the amount of liquid that passes through some like slice in a certain amount of time. And this is a constant in a closed system. Because if it wasn't, where the heck did my fluid go? And there's a bunch of crazy equations here. I'm going to reference those in a second. I'll chat about those in a second. But for now, I want us just to understand the idea of flow, this like first part. Q equals V over T, volume over time. That's what I want to emphasize. That's the definition of the word. And then these other ones are really straightforward, but one thing at a time. So again, let's look at our example. Let's say at some point I measure the flow rate as 3 liters per second. It literally means every second 3 liters passes this line. That's the definition of it. Every second 3 liters of water passes this point. That's how much water is kind of moving. At a later point in the pipe, what's my flow rate there? It's also 3 liters a second. And the logic here is, what if it wasn't? What if it wasn't? Let's say it was 1. That means at this point, 3 liters passes this every second. At this point, only 1 liter passes every second. That means every second I have 2 extra liters that where the hell are they going? Like 3 come in, 1 come out. How does that make sense? Another analogy I give you all is like this room. If 50 students come in my room, 50 students better leave my room. I don't care what doors students leave my room, but 50 students are going to leave if 50 students come in. If 50 students don't leave, then I have some extra students left in my room and I don't know why they're still here, kind of thing. If I have 3 liters come in, I better have 3 liters come out. Otherwise, where do the other liters go? Where do they go? Is basically the question. So this is the idea with flow rate. This is the idea that it can't change. It's a constant everywhere. And this is true in your body. The amount of blood passing through your heart, there's a flow rate to that. All the blood has to at some point pass through your heart. The flow rate through your heart, if you take all the arteries that stem off that, the flow rate's going to be, if you add up all of those, it'll equal the flow rate of the heart.
Does the fluid have to be ideal? Or no?
No, the fluid doesn't have to be ideal. Well, it needs to be incompressible. The only requirement is it needs to be incompressible. And the reason is, if the flow rate's not a constant, that means somewhere in your body, fluid is like depositing somewhere. Yeah, literally like, so let's say I had this scenario. I measure the flow rate at 3 liters per second at the beginning, and I measure it 1 liter a second at the end. You know what that tells me? That there was another path somewhere that the fluid could go down. There's either a leak in the pipe, or there's literally a separate junction that in this junction maybe 2 liters per second are going through. That's the only way it's possible. The fluid has to go somewhere. So, anyway. All right, I thought I saw a question somewhere in the middle. Yeah.
So you said in our blood pumping through our bodies,
Yeah.
the flow rate is constant.
So it's, and the key here, and I actually have a question. Let's see if it's the one I picked. No, I didn't pick it here. There's one caveat to this. Well, it's not necessarily a caveat. I actually asked this question on the quiz. Let me give you all a separate example here. Let's say this is your situation. If it splits, if this side is 1 liters per second, how much is going to flow through my other side? Yeah. So it doesn't mean that every branch has the same flow rate. It just means that all of them together should equal what I started with. And then if these come back together, it turns back to 3 again.
So regardless of how fast your heart is beating, as long as the system is closed, it's always going to add up to the same number.
It does matter how fast your heart's beating. We can take the extreme. If your heart stopped, your flow rate's going to turn to 0. So your hearts can increase the flow rate, but then all the arteries that stem off it, if you added up the flow rate of all those, that would equal the flow rate of your heart at that moment, at that exact moment. Yeah.
Would there be any case where the flow rate will increase instead of decrease?
The rate, the flow rate?
Yeah.
Yeah, so the question was, is there any case where the flow rate might, and so in this example, I guess it kind of, each branch had a smaller one.
Yeah, but like the overall.
You could have the opposite. You could have 2 branches go into 1, and then the flow rate. Think of a river. You got a bunch of streams flowing down mountains. They all collect in the river. All their flow rates add together to make the flow rate of that one river. Yeah.
With like what you were saying about the heart and like it stopping.
Yeah.
Is that the reason why you like breathe more when you're working out and your like heart rate increases to keep everything constant?
My best guess for the reason you have to breathe more is if your heart's pumping, you need more oxygen.
Yeah.
And so your heart's going to pump quicker. Your blood can only carry so much oxygen. So the faster you move the fluid, the more oxygen you can get to a location. But you need to supply that blood with enough oxygen to keep up with demand. So that's more, I think, more like a supply and demand kind of situation where your body's demanding more oxygen. The only way you can get more oxygen is if you make the blood flow quicker, but then you need to supply the blood with more oxygen. So it actually, yeah, that's my best guess. That's a good question. So yeah, what I really hope though is that you all understand intuitively is flow rate. Literally think of it like cars on a road. If a road splits, some cars go some way, some go the other way, but you still have the same amount of cars. And the flow has to stay the same everywhere. This is a really important concept for physics 2. You are going to learn in physics 2 about electricity and something called current. Current is the flow of electricity. It's literally how much charge per second. Instead of liters per second of fluid, it's charge per second. And it's the exact same idea. When electricity splits, the amount of current going in will split in some way. But the amount of current in a path will be the same, just like the amount of flow in a river will be the same. So if you all can understand this, it's going to prepare you really well for current. That's why this idea is useful. All right, now to point out these equations here, they're really straightforward. If y'all remember, we did this before. Volume is the same as area times the distance. That was, here, let me just jump up to this. At some point previously, I asked you all this question. What's the relationship between volume and height? If you just replace the letter H with the letter D, it's the same thing. So volume equals area times, if you all look at this picture here, it's just a cylinder on its side. Area times distance gives you the volume. Distance divided by time is velocity. Great. Why does this matter? If the flow rate is a constant, Q1 equals Q2, then you just swap in A times V equals A times V. And this is why when you put your finger over a hose, it sprays out faster. The amount of water still got to exit. The amount of water going through your hose is set. When you put your thumb over it, the same amount of water has got to go through it. Otherwise, your hose is going to explode. And so, yeah, this is the relationship between area and velocity. You made the area smaller, you made the velocity go up. Great. So it's something you are familiar with. Now you know the reason. You can try to explain it to others, see if they'll be patient enough to listen. All right. So here we go. Yeah, this one does have it splitting. So as blood passes through the capillary bed in an organ, the capillaries join to form venules. If the blood speed increases by a factor of 4, and the total cross-sectional area of the venules is 10 centimeters squared, what is the total cross-sectional area of the capillaries feeding them? And then if each capillary has an average diameter of 10 micrometers, how many do you need to make this happen? It sounds really fancy. If we draw a picture of this, it's not going to seem as intimidating. You got a bunch of pathways, bunch of capillaries. They all join together to make one big. So you got your venule, and then you got 1 capillary, 2 capillary, 3 capillary, 4 capillary. I don't know. I don't know the answer of how many yet. So I'm just making up a number. These are moving, and then it's moving in there. So start with, we drew our picture, ready? What are we solving for? What do we have? What equation relates those things? And go from there. You all are very capable of doing this.
Which one of those is the 10 centimeters?
The big boy.
The big one. Okay.
Yeah. It's asking for all of them together.
But at some point it speeds up by 4 times. I'm also not sure which one it speeds up by 4 times. It's too heavy for this.
So we start in the capillaries and we end in the venule. So all right, so let's. Oh, that's fine. You don't need to. I don't know what these were like. I kind of remember. I don't know where I learned capillaries, but that one I know. And I know arteries go away from the heart and veins go towards it because of the A. Super nice. All right, what are we even solving for, y'all? Yeah.
We want to see how much pressure is in the.
We want to know something about the capillaries. We want the. What is the total cross-sectional area? Yeah. Now, is this where I start or where I end? It's just convenient to label this as 1 or 2. It's where we, yeah, this, remember, it says the capillaries join to turn into the vein. I could. I'm not gonna have a question this contextual on the test. On the test, it's just gonna be a bunch of pipes. It could be a river. 2 rivers join. That's fine as well. I will warn you on the quiz, there is another medical context one. It's fine. All right. We're solving for the total area. The total area of all of them together. Do we care that there's a bunch of them? No. Not really. Not yet. We do for part B. Basically, we just say we got a bunch of these things. If you added up all their areas, what would it be? Great. All right. What do we know? We know area 2. Good. We know area 2 is 10 centimeters squared. This is one of those cases where you technically don't need to convert units because it's a ratio problem. But again, if you're not sure why we don't need to convert, just go ahead and convert. It doesn't take that long. Remember, we got to do the conversion twice because it's centimeter squared to meter squared. All right, there's one more thing we know. Don't know the time. That's a good guess, though. There's another number given. So it says if the blood speed increases by a factor of 4. If something's increasing by a factor of 4, if I have a mass of 1 kilogram and I increase it by a factor of 4, what's my new mass? 4. It's just 1 times 4, right? What if instead it was 2 and it increased by a factor of 4? It'd be 8. So how do we write this? We don't know V1. We don't know V2. We know the relation between them. We know that the blood speed increases by a factor of 4. So my new velocity is 4 times my original velocity. It's 4 times bigger. So it's taking a idea and expressing it in variables. A relationship expressing in variables. All right. And then hopefully we just had the last slide, so I think you all can guess what equation we're going to use. Try it. Try it out. See if you all can figure out what to do to solve for area 1.
So if we're trying to find a cube, the area of
When they got a small too.
Oh, and if you want the answer, it's 2.5 centimeters squared, I think. No, maybe. Wait. Let me make sure I'm going the right way. I don't want to lie to y'all.
I did the same.
Oh, I totally lied to y'all. 40 centimeters squared. Yeah, no. I went the wrong way. That's what you get for doing it in your head. That's what I get for doing it in my head.
Yeah, the one doesn't even matter, so.
That's why you should get to kind of put this out.
Job. You're smart.
All right. So, what's going on here? I drew my picture. I drew my picture as a bunch of capillaries becoming one big tube. Something I want to challenge you to is to realize the way we're setting up this problem, we're basically, so when it comes to flow rate, we can basically take all those small tubes and actually pretend like they're one big tube. We can pretend like this problem, which has a bunch of small tubes, is one big tube. And that's what's going on here. Why did I draw it this way? Did it get faster or slower? It got faster. So what we're doing is we're taking all these tubes and we're basically taking them together. Again, I'm going to keep mentioning the car analogy. Say I have 5 single lane roads and then they turn into a double lane road. So I have 3 single lane roads turning into a double lane road. You know what's another way of thinking about this? Another way of thinking about this is that I have a 3-lane road turning into a double lane road. Flow rate doesn't know that they're separate pipes. You can basically pretend like it's one big pipe. You can take all those capillaries and smush them together and pretend like they're one big old thing. So that's the idea. Whatever. It's not super important that you all... What you need to know is just the flow rate stuff and all that jazz. So, all right. Great. So I kind of wrote the equation here. I rearranged it for A1. So A1 is going to equal A2. And then what we do is we just take this nice little ratio and we chuck it in here. So it's going to equal 4 V1 over V1. And I have a V1 on top, V1 on the bottom. They go away, and you get an area that's 4 times bigger. If my speed goes up, then my original area had to be larger because it was slower there. So yeah, you get A1 equals 4 times 0.001, which is 0.004, which is meters squared, which is the exact same thing as 40 centimeters squared. All right, so that's part A. Part A just, it's flow rate. Part B, how many capillaries do you need to get this area? And so I give you the diameter of each capillary. A capillary we assume is a circle, like pretty much all pipes are circles. I give you the diameter of each capillary. How many capillaries do you need to make this area? Again, basically like how many single lane roads do I need to make a 40 lane kind of sort of? The answer is not 40. Don't say it's 40. These aren't single, like you got to figure out the size of each of these. How many of these do I need such that if I smushed them all together, it made a total area of 40 centimeters squared? The answer is going to be a lot. Also, if you don't know this micrometers thing, that's fine. We haven't used it. I'll write this for you all. Micrometer is 10 to the minus 6. It's small. So I'm going to steal all my stuff from the last slide. So like from the side, it looks like this. How many of these little dinkers do you need to fill the void?
I want to make sure that I answer that before I go talk to anyone.
Yeah, c pi r squared, you converted it. Good. Good. You need 40 divided by that.
Okay, wait. Okay,
Yeah. No, that I can make sure here. I don't know what the actual answer is, but your process is good. And that's the most important thing is your process, because that's what you're helping people with.
Okay, cool.
Yes, that's why I started. Why not? What happened? How?
All right. The answer I got. How many do you need? 5.09 times 10 to the 7. You need a stupid number of capillaries. I don't actually know if this is a reasonable number or not. This is such a silly large number. So, if you look at kind of the picture here, basically this big old circle is 40 centimeters, or 40 centimeters squared, or 0.004 meters squared. How much area does each capillary?
I was looking at the 10 centimeters cubed.
Oh,
Not the, okay.
yeah.
Radius is pi.
I have no idea if this is a reasonable number.
Capillary is also small.
They are small, but this is like 2, 3, 4, 5, 6, 7. 50 million capillaries. I don't know. That seems a little silly. Is that reasonable? Y'all, is there billions of capillaries in the body? Oh, great. Okay, it's reasonable then. Maybe. Which is wild that your body has this network of roads in the body. Yeah, it's nuts. And you can think of them like road. Like, if you understand roads, you can just think of capillaries and flow. And yeah, I mean, that's... And they turn into one big old road. But I mean, that's the idea. So the key here is you got this big old area. What's the area of a single capillary? That's the key. What's the area? How would I find the area of a single capillary if it's a circle? The area of one capillary is pi times the radius of the capillary squared. Great, that's one of them. If I know the area of one of them, then the next question is how many do I need to get to the 0.04 meters squared? 0.004 meters squared. That's the trick here, y'all. If I have 60,000, yeah, whatever. I was like going to come up with some weird elephant example. Did that? Yeah.
I was using diameter.
The classic. Yeah. Yeah, the classic here is make sure you're using radius and not diameter. It's a classic. Classic test boo-boo is they give you diameter and you got to convert to radius. Super, super normal. Always happens. Doesn't. As time goes on, you still make those kind of mistakes, but just kind of less of them. Like in physics, it's so common. Like, it shows up all the time where they give diameter.
Yeah, mine's also. Well, you have 7. Oh, mine is in centimeters. So I did to the negative. So I have the area. And then I got that number. Wait, so what you got from centimeters?
Yeah.
I got what I did was, I put -6. So that times 0. That's how I got that.
All right. And so there's the full problem worked out. And so what's interesting here is in each capillary, the velocity will be 4 times slower than in the big vein. The velocity does slow down because there's so many of them that their total area together is 4 times bigger. Now, again, I don't know how accurate these numbers are, to be honest. But that's the interesting thing with this thing is you basically take all these capillaries. Yes, each individual capillary is small, but there's a ton of them. There is so many of them. Again, it's like taking a 2-lane highway and it splits into 8 individual single roads. I can fit a lot more cars on 8 individual single roads than I can to a single 2-lane highway. That's the idea. And so in each of those capillaries, the velocity will be 4 times slower because the total area of all the capillaries together is 4 times bigger. So you don't actually care about the size of each individual capillary. You care about their size times how many of them you have to get the total area and yada, yada, yada. So, yeah, it's just one of the things. Whenever something splits into many objects, and again, one of the quiz problems is going to be on this, so it's a good practice one. Instead of splitting into 50 million, I just have it split to 2. I have an artery that splits into 2 branches, and it's a similar idea. And I say, hey, I got some area of an artery. It splits into 2 other arteries that are each this area. Find the velocity in each of these small arteries. So it's a good practice one for this. All right, and then I have one more thing to teach you. And it's going to be something that's going to be, I already mentioned it to y'all. It's not intuitive, but it's okay. Because the equation for it is going to be something that I hope at this point you're very comfortable using. Because it's something you've been doing a bunch with a new paint job. Energy. Don't worry, you will see kinematics with a new paint job after test 2. Yeah. All right, it's Bernoulli's equation. It's conservation of energy for fluids. I hope when you all look at this that you're not like, oh my gosh, that looks like nothing I've ever seen before. If you feel that way, yeah, I was like, I hope after you do enough energy problems you realize 1/2 rho v squared, what does that really look like? That really looks like 1/2 mv squared. What does rho gy look like? mgy. Fun fact, this equation is conservation of energy. All you have to do to turn this into conservation of energy is divide every term by volume. This equation here, and I'm going to show you all this very quickly because it's very simple to show. If you divide every term here by volume, everything gets divided by volume. You're allowed to do that to an equation. Remember, y'all, rho equals m over v. If you rearrange this, m equals rho over v. Nope.
Rho times v.
Oh, did I do the wrong thing? I'm supposed to multiply by volume. Oh, I said the wrong thing. I'm sounding like a chump. Mass equals rho times. If you multiply everything by volume, rho times volume is mass. So this turns to mass, this turns to mass, this turns to mass, this turns to mass. Yay! What about this term? Volume times pressure. Volume times pressure, all right? Remember, y'all, pressure is force over area. So that equals V equals force over area. Remember, y'all, that volume equals A times the distance. Like if you had a cylinder that's on its side. Remember, so A times distance times force divided by area. Oh my gosh, what's force times distance?
Work.
It's the work done. If you just multiply every term here by volume, it turns into conservation of energy for normal mass. So it's a really easy, I'll leave all that nonsense there. All right. So, why does this matter? If you have okay. So there's gonna be something really counter to. Oh, I put divide everything. Ugh.
If you take conservation of energy and divide, you get that.
Oh, okay. Great. So I'm still okay. Great. I'm fine. It's fine. All right. So great. If you are cool with conservation of energy, it's the same thing. You just use fluid stuff. And all right. So now I have a question for y'all. If a fluid starts and ends at the same height, but its velocity increases, what happens to the pressure? Look, I'm going to write the equation for you all. Before you even start this, before you answer this question, we're going to use this equation to answer this question. So it's conservation of energy but for fluids. It's called Bernoulli's equation, named after the guy Bernoulli, who just discovered it. Shock and awe. All right, so check out this equation. If I start and end at the same height, do I care about my gravitational energy terms? Again, these technically aren't energy, but you can kind of think of them like that. So use this. If my final velocity is bigger than my initial velocity, how is P1 and P2 going to compare? If this term, the final velocity term, is bigger than this term, what's going to have to be true about P1 and P2 to make that happen? Make up numbers if you want. And I put PF and P initial. PF is P2. P initial is P1. Just to stay in that mindset of initial and final. Again, make up numbers. Make this value some number. Make this value some number. And see if your logic works. If you don't do that, you are very likely going to make a mistake.
Yeah.
Oh, it's higher than the final.
Yeah.
Oh, yeah.
Oh my God, that's beautiful. What?
That's crazy. That's crazy.
All right, we'll go like 15 more seconds.
Okay, hold on, I was ready. Okay. 407. Yeah. 802. Awesome.
And again, just to like help people make this as explicit as possible. Which one's bigger, final velocity or initial? Final. Make this number 10. So P2 plus 10 equals P1 plus, pick a number that's less than 10. Great. You tell me how these numbers have to compare.
Oh, I put 2 L's instead of 2 A's. The dyslexia is acting up.
All right, 5 more seconds. 5, 4, 3, 2, 1. Ciao. All right, let's make up a number for P2. Why not, right? Give me a number. 6. Great. If P2 is 6, what is P1 going to have to be to make this relationship true? 11. 6 plus 10. So long story short, and this is the thing that's really weird, when you go faster, your pressure goes down. When you go faster, the pressure goes down, which is totally not intuitive. In my opinion, this is not intuitive at all. But according to conservation of energy, it's got to be true. Now, I've heard some, I was trying to look up things to try to give you all a conceptual kind of explanation for this, and I found a Reddit post, and someone made an argument, but then someone refuted them. But I think their argument, I don't know if it's true, but it at least maybe makes it feel better. So let's say you have a system. I just need some space. So you got a pipe, and the pipe goes down. Great. So here you got some velocity, here you got some velocity. When you're in the smaller pipe, you're going faster, right? Like, we're cool with that, hopefully. This is terrible. My picture here is trash. All right, great. You go faster. What's required to go faster? If you had some object, what would you have to do to it to make it go faster? Just like literally any object in the world. You want your car to go faster. What do you need to do? You got to speed it up. How do you speed it up? What do we apply to something to speed it up? A force. You apply some force to it. But the problem is that's not free. So the logic that I heard someone else say, okay, the logic I read online, I don't know if it's true. I don't have it in writing. I have to think about this more. Originally, this is pushing outward on the vessel. So how do you make it go faster? The argument someone made was like, oh, we take some of this pressure that was pushing against the containers, and we use that pressure to kind of push it forward. So we kind of steal some of that outward pressure and redirect it forwards to make things go faster. And the end result then is my pressure is lower. I kind of redirect some of it forward. I don't know if it's actually an accurate explanation, but it might kind of make things feel a little bit better. Instead of this outward pressure, we kind of direct it forwards, reducing the pressure but increasing the velocity. Whatever. This has lots of consequences. Well, okay. I say it has lots of consequences, but then also people disagree on whatever. So a few cases of this can be used to explain why planes fly. I prefer a different explanation, but this is fine. At the top of a wing, the velocity of the air is just a fluid. The velocity of the air is faster, so you have a lower pressure. At the bottom, the velocity is lower, so you have a bigger pressure. If I have two different pressures acting on the same area, the bigger pressure is going to result in a larger force, i.e. make plane go up. Like, if you have a bigger pressure on one side, it's going to make things move in that direction. Fun fact, a sail is just a sideways plane wing. It's the same thing, just sideways. And so this is another way that boats can they can tack into the wind is an interesting thing. Another one, and this one's not. I wish it was totally valid. But if you blow over a piece of paper, the paper will lift upwards. And you can use Bernoulli's, but then it kind of doesn't work. So it's very sad that one doesn't work. But yeah, long story short though, as velocity goes up, pressure goes down. I found a really good application of this, and I made a problem based upon it. It's the echocardio. I've mentioned it so many times. This is how echocardiographic exams work. Echocardio. Oh, it's so long. Do they have a short name for this? Great. ECG? EK. Why do they say K? Oh my gosh. Okay. All right. EKG. That feels bad. There's a C here. But, at the same time in physics, we use the wrong one. Yeah, we do the same thing. All right. Whatever. And an EKG, this is how they measure the pressure in the heart. How do they measure the pressure? They don't measure the pressure. they measure the velocity of the fluid. Using an EKG or whatever device they use for this, I don't know if they use ultrasonic or whatever, they're able to measure the velocity of the fluid. By measuring the velocity of the fluid, they can in turn measure the pressure difference. So let's do that. So you're not finding the pressure itself, you're finding the difference in pressure between the two sides. When they do an EKG, they're finding the difference in pressure. And if that value is a certain amount, it's bad, I guess. Yeah. All right, so it's not the same thing. I'll have to use the whole word. An echocardiogram. It's so long. Just call it an echo? An echo exam. Great. But then that's probably related to hearing too. It's fine. Everything's fine. All right, I'm going to try to draw a picture of this. It's going to be great. Here's your heart. Oh, there it is. Oh, it's terrible. There's the heart. You got two chambers. There's the right side and there's the left side. Oh, nope, they're both on the right side. Hate that. All right, there you go. The right ventricle, that's that one. Right ventricle, that's the right atrium. Totally, this is not good. So good, right? All right, and then it's moving here, and it's not moving in the other one. Wow. What a good picture. We're going to say that the height difference is negligible between the two because basically we're considering this interface. Now it looks like a Pokeball. If we're considering the interface between the two, there's a kind of like this zone. This distance between the two is like nothing. We take just that little. They're measuring the change in velocity between 2 points on one wall and the other wall, and basically the thickness of that wall is so thin that we can ignore the height difference. If you really want, you could consider it, make it like 0.0001 meters, and it doesn't change anything. So yeah, try it out, y'all. It's using Bernoulli's. It's just a conservation of energy problem, but with fluids. Instead of work, you got pressure. Instead of mass, you got density. That's the only change. Sorry. It's really weird. I can't actually tell. Like, I don't hear it. It's bad. My apologies. Yeah, one is one side. Yep, one is the beginning, one's the end. That's the whole idea. You start somewhere, you end somewhere else. No. What are you solving for? Always keep your eye on the prize. How would you write that mathematically? Yep. 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 Density is what? Density is pressure.
Pressure is a cause of density.
That's one way. We've also now learned that you can also change pressure by changing your velocity. So there's two ways you can change your pressure. Yeah. No, you're good. But that's cool. And it actually reminded me that like this equation I just showed you all includes what I taught you before. One way to change your pressure is to change your height. Another way to change your pressure is change your velocity. Now we put them together.
That wasn't sarcastic. I don't know why I came out like that. No, it wasn't cool.
All right, what are we even solving for? If you don't know what you're solving for, you can't solve it. So, yeah, what wording in the problem? It says, what are we finding? The difference in pressure. What does the word difference mean mathematically? Subtraction. Let's write that out. What's my variables for those? You got a P1, you got a P2. We're solving for the difference. If you want, you could say final minus initial. If you prefer. If you want to keep it like in energy terms, what's my pressure at the end? What's my pressure at the beginning? And someone else also pointed out something really interesting that I should have noted before. If you all look at this equation, this rho GH this rho GY is something we've seen before. If we scroll way up here, remember, one way you can increase your pressure is to change the height. That's one way you can increase the pressure. That shows up in Bernoulli's equation. What's one way you can change the pressure? Change the height. And then the addition is what's another way you can change the pressure? You can change the velocity. And it puts it all together. So that's the cool thing with this equation. There's just like there's when we do energy, we got both terms. All right, great. So we're solving for final minus initial. What's given? Initial or final?
The initial is 0.
Nice. My initial velocity is 0. Final is 3. And then I'll chuck it over here. We know the density of blood is 1060 kilograms per meter cubed. And then we also know the difference in height is negligible. So we're not increasing pressure because we're going farther down or decreasing pressure because we're going up. So we ignore height. So yeah, then it's just, I'll write out the entire thing. P naught plus 1/2 rho V initial squared plus rho G Y initial. It's just conservation of energy, y'all. And we ignore these terms because it's like a car on flat ground. If a car starts on flat ground and ends on flat ground, its energy didn't change. Again, these terms aren't technically energy, but I'm going to keep referencing that because it's the same process. Obviously, pressure is not energy, but it's the same thought process as energy. So yeah, you just solve and get an answer, and what's the answer going to be? So yeah, I'll solve it out and I'll check. I'll do the calculations real quick just to double check. And make sure you know the right units. Let's see, did I? Yeah. My pressure went down. This does not say I have a negative pressure. It's a difference. It says my pressure went down. Why did it go down? Because we went faster. The faster you go, your pressure is going to go down. Now, this answer is in pascals. That's the other thing. If you tried to tell me that this is millimeters of mercury, that person is like not okay. So convert this. Convert this to millimeters of mercury. See if you remember how to do that. I'm just going to show you the answer for that. Because in the medical context, that's what you're going to actually spit out. And yeah, this is a real thing that is done. And this is how an echocardiographic exam is done. They measure the velocity of the two fluids. They do Bernoulli's equation. and you get the change in pressure between the two areas. And ostensibly, you don't want that pressure change to be too big. If you have I will say from a physics standpoint, yeah, if you have a large pressure imbalance, that's going to be a lot of force acting between those two things, which is not good for your body. So yeah, I'll quickly write out the last answers here. So in case you didn't, the initial velocity is 0. If you rearrange things, it turns to a negative, which is going to equal negative 1/2 times 1060 times 3 squared. So the math here is very easy. Any problem I give you all with Bernoulli's is going to be like energy, where energy is very straightforward. The math, it's just like a one and done generally. Energy is great. Hopefully you've done enough energy to realize that it's like the easiest thing in my opinion, it's the easiest thing. I keep trying to sell that. We'll see if you believe me or not. It's not vectors. Rule of thumb, if you're not doing vectors, it's usually less math, and people like that. Physicists love energy. My gosh, do we love energy. It's like you can explain everything in the universe by saying things want to go to lower potential energy. Every single thing in the universe can be explained with that one statement. All right. So yeah, there's no lab today because I have the plague, and it seems like Peter may or may not also have some form of plague. So we're not going to get you all sick before spring break. You're welcome to stick around, and we'll help you from a distance. I still technically have office hours. I've had people come by. They haven't caught the plague, so it seems to be fine. I keep my distance and all that. But have a good spring break, y'all. I'll see you on the other side. Test will be Thursday when we get back. Note cards are up here if you want one.
Have a good night. Feel better.
Karate Kid.